Okay, let's talk about moments and center of mass. So let's say that we have some masses. We're imagining that we have these are like points, but each one has its own mass. So we have n points, and the ith point has mass m sub I, and we're going to start with just a one-dimensional problem. So we're going to imagine that these points are just on a number line, and the coordinates, there's just one coordinate because it's a one-dimensional problem. So our mass m1 is at a coordinate of x1, m2 is at a coordinate of x2, and so on. The center of mass, and this is like a physics concept. One way of thinking about the center of mass is like if I were to put my finger somewhere on the line and expect this to balance, because each one of these things has some weight, and I want to balance it on my finger, and where I would put my finger to balance it would be the center of mass. Another way of thinking about the center of mass is if I were to take this and spin it, it would naturally want to spin so that there's like a particular point that stays fixed and everything else is just rotating around that point, and that point would be the center of mass. And so the way you find the center of mass, this is just a formula, but let's make sense of this formula. This is like a weighted average. If we imagine, for example, that all of these m sub i's were just 1, then the top of the fraction I would just be doing, 1 times x1 plus 1 times x2. So in other words, I would just be adding up x1 plus x2 all the way up to xn. And on the bottom, it would be, 1 plus 1 plus 1, n times, so the bottom would just be n. So that would just be the average of all the x's, right? Like I would be adding x1 through xn and dividing it by n. That's what we call an average. And that makes sense. If all the masses were the same, then none of these points is like more important than any others, and we just have the average of the x-coordinates. If the points have different mass, then the heavier ones are more important, so to speak. And so what this is it's a weighted average where it's like an average where the heavier things take more weight. Anyway, so let's call the top capital M. So I wrote it this way. This is just using sigma notation, but this is the same thing as the top. And then let's call the bottom little m. That's like the total mass of the system. So I wrote it with sigma notation as well. All right, so that was just a one-dimensional problem. In 2 dimensions, it's actually not so different because we can handle each dimension independently, basically. So if I have my masses m1 through mn, and this is now a 2-dimensional problem, so my mass m1 is at a point x1, y1, and so on. So each m sub I is at a point x sub I, y sub I. And I drew a picture here just for the sake of having a picture. But the point is, if I want to find the center of mass in a 2-dimensional problem, and just to keep things concrete here, this basically means if my xy plane was like, let's imagine that it's like rigid, but that the xy plane itself doesn't have any mass, and the mass is at these points. These points are the only mass involved here. And if I were to put my finger underneath the page and want to balance this mass on my finger so that it's not like wobbling this way or this way, where I would put my finger to make it balance is the center of mass. Similarly to last time, another way of thinking of it is if I were to spin this, then there would naturally be a single point that stays fixed and everything else is spinning around it, and that point is the center of mass. And the nice thing is, we can basically just treat this as two independent, one-dimensional problems. So I can find the x coordinate that is like I can find the x coordinate that would balance on a vertical line. So it's like if I were to move my pen to the left or to the right, and I want this system to balance on my pen, and all I have to worry about, because I'm doing a whole line here, I'm not trying to just balance it on a single point, I just have to make sure that it doesn't wobble to the left or wobble to the right. And the way I do that is by treating this as a one-dimensional problem. So all I'm really trying to say is that the x-coordinate of the center of mass is this, which is the same formula that we used when it was a one-dimensional problem. Similarly, to find the y-coordinate of the center of mass, this is like trying to balance on a horizontal line where all I have to worry about is that it doesn't wobble like this way or this way. And I find that by looking at the y-coordinates, and I just basically use this same formula, except now I have y's instead of x's. So the center of mass is, I'm just summarizing this up here, and we're using some notation here for it. So I'm going to call this top m sub y, which is a little bit of a confusing thing to call it because this is like using the letter x and this is like using the letter y, and yet we call this thing m sub y and we call this thing m sub x. I mean, the letters are switched basically because for m sub y, that's like when you're trying to balance it on a vertical line, and vertical lines are sort of associated with the letter y, and horizontal lines are sort of associated with the letter x. But anyway, we define m sub y to be the numerator of this fraction, which has the x's in it, and we define m sub x to be the numerator of this fraction, which has the y's in it. We define little m to be the denominators, which are the same thing. Little m is just the total mass. Okay. So let's get to something more calculus-y, because I would like to find the center of mass of a region, like the region bounded by y equals f of x. So let's go over how to do that. You might guess, since this is calculus, we're going to approach this by breaking our region into a bunch of little rectangles, and you would be right. So the way we're going to treat this is each one of these rectangles has its own center of mass. But what I have to do, or let me expound on that. Each one of these rectangles has its own center of mass, and it's very easy to find the center of mass of a rectangle, just intuitively. The center of mass is like like the x-coordinate is just halfway in between the two x-coordinates, and the y-coordinate is just halfway in between the two y-coordinates. It's the point right in the middle of the rectangle. Of course, yeah, maybe I should actually draw the rectangles. I drew the partition, but let's imagine that we sort of cut these rectangles off somewhere in each one. So something like that. Right. So each rectangle has its own center of mass, and we have to put that together and find the center of mass of the whole thing. So here we go. For the ith rectangle, the center of mass is the x-coordinate for the center of mass of the rectangle is just the midpoint. Like if I'm looking at the first rectangle from x0 to x1, the x-coordinate of the center of mass is just the average of the two endpoints. And so in general, the ith rectangle has endpoints x sub I minus 1 and x sub I, and I would just do the average of those. So that's the x-coordinate of the center of mass of a rectangle. The y-coordinate, I just look at how high the rectangle is, and I cut that in half, and that's this. Okay. The amount of mass in a particular rectangle is basically its area. By the way, we're assuming that this region has uniform density, meaning that every bit of it is as dense as every other bit. We don't have denser parts and less dense parts. It's all equal density. So the amount of mass of a particular rectangle is just whatever the density is times its area. And the area of the rectangle is just length times width. So the width is what we call delta x, and the height of the rectangle is this y coordinate. So that's like f of this x. And okay, so here comes the part where we imagine the rectangles becoming skinnier and skinnier, and then we write a sum which turns into an integral because the rectangles are getting skinnier. Here we go. So let's talk about these numbers my, mx, and m from the previous page. Right. So to get my my, I would add up each mass times the x-coordinate. So I'm going to add up, let's see, here's the x-coordinate, and then here's the mass, right? Like, here's the x-coordinate for the center of mass of the ith rectangle, and then here's the mass of the ith rectangle, which is just taken from right there. So that's what we're adding up, and we're just using this formula. Okay, so what is this? I just rearranged it. I can pull a row out of the sum because the row is a constant, it's constant density, and then I just sort of rearranged it to put the delta x last. And we've done this a million times. We have a sum with a delta x in it, and delta x is going to 0 because the rectangles are getting skinnier and skinnier. This sum turns into an integral. The row stays on the outside. The function that we're integrating is basically this function, so it's like x f of x, and I integrate from a to b. Similarly, we can do m sub x, just using, what did we say m sub x was? We said m sub x was the sum of m sub I, y sub I. So I will take, let's see, here is my y sub I. That's just taken from here, right? That's the y coordinate of the center of mass for the ith rectangle. And I multiply that by the mass. That's the same as it was above. The first part's different, but this is the same. And then the rectangles get skinnier, and this sum turns into an integral in the same way. So I pull the row out, I've got a half, and then there's this f of x and this other f of x, and so I've got the integral of 1/2 f of x squared. And then similarly we can do little m. Maybe I should have done little m first because it's the easiest one. But for little m, I'm just adding up, well, again, I can point to this page. I'm just adding up all the masses, and I don't have to multiply it by an x or a y. So I'm literally just adding up all of these. So I just put this inside of a sigma, and then the rectangles get skinnier, and the sum turns into an integral, and this one's just the integral of f of x. So what we get out of all of that is this formula for the center of the mass. Because the center of mass is, I can refer to this page again, I do my over m and then mx over m. And when I do that, all of these have a rho, and the rows just cancel. Of course, the center of mass shouldn't really depend on the density. Like whether we're talking about a very heavy density or a very light density, the center of mass should stay the same. It's just that the total mass of this may increase or decrease if you mess with the density. But the center of mass doesn't change, so it makes sense that it would cancel. Anyway, so the rows cancel, I just get this integral over this integral, and that's this. And for the y-coordinate, I get this integral over this integral, and that's this. Okay, we are totally going to do an example, but let me just real quick go over a slightly more general situation. So we just did, when the region is like this, like there's a single curve, y equals f of x, and I'm just doing a region like this. Let's talk about if there's like a curve on the top and a curve on the bottom. Like the bottom isn't just the x-axis, it's some other curve, g of x. And I'll just go quickly. It's sort of what you might think. It's generally going to remind you of like taking what you would get from f of x and then subtracting what you would get from g of x. So we define A. By the way, A is just the area of the region. It's the integral from a to b of f of x minus g of x. And back when we were doing the previous example, and basically our g of x was 0, this was our A, because g of x was 0. But now g of x isn't 0, so this is our A. And I don't know, maybe I don't want to explain this much, but for our x-coordinate, I get 1 over a times this integral, which is like a generalization of this integral. Like this was when our g was 0, and now our g isn't 0, so we get this. And then for our y-coordinate, we get this, which is like how this generalizes. That this was when g was 0, and this is when g isn't 0. Anyway, let's find a particular center of mass. So one thing I liked about this is it's sort of intuitive. You can visualize where the center of mass is and sort of tell whether it's believable, or, you know, if you find a center of mass and you look at the graph and it's way, way off, you'll probably be able to tell. One example I was going to do, and I decided against it, was I was going to say, let's find the center of mass of a circle. Of course, the center of mass of a circle intuitively should just be the center of the circle. And if you use these formulas, it's a bit painful, but you will find that the center of mass indeed is the center of the circle. But I decided against doing that example because it's, I don't know, those things are fun because you know what answer to expect, but I decided to do something else. Let's find the center of mass of this one. And before I do anything, let me just have some intuitive discussion. For example, I would say for the center of mass of this one, I'm going to say it should be farther to the right than to the left. Like, this goes from -1 to 1. So in some sense, it's like horizontally, it's symmetric, just in the sense that I go as far to the left as I do to the right. But that's not really telling the whole story, because I can see that I have more stuff to the right, like the graph is taller. And if this is uniform density, the stuff to the right of the y-axis Like if I put my hand right here on the y-axis, there's definitely more weight on the right than there is on the left. So I'm going to guess that the center of mass is, I don't know exactly where. I don't trust my picture quite enough to say exactly where, but it's going to have a positive x coordinate. In fact, I might guess that the center of mass is maybe somewhere like there-ish. It's believable that if I were to put my finger right there, that it would balance. Of course, this all depends on how much we trust my picture, which is probably questionable. Anyway, let's actually find it using some formulas. So, let's find my A. So I can just use this formula. Of course, in this example, my g of x is 0, so I could use the first set of formulas, but it's also fine. Like I can use these formulas and just use g equals 0. So like that. So this isn't hard. So antiderivative is just e to the x, and so this is e to the 1 minus e to the negative 1. Now, let's find this integral. So I've got this. And this is going to be integration by parts. Oh, whoops, I did not. I should have filled in minus 1 and 1. Yes. So this is going to be integration by parts. Like that. du is dx. V is e to the x. So we're going to get, this is u times v minus the integral of v du. So I've got this. So let me go back up, because I have to do my limits of integration. Oh, and I guess I don't need this plus c after all, because I have limits of integration. So here's what I'll write. X e to the x minus e to the x, negative 1 to 1. So what do we get? When I plug in 1, I get e minus e. When I plug in negative 1, I get negative e to the negative 1 minus another e to the negative 1. So this gives me 0. This gives me 2e to the negative 1. Okay? So where are we? We found A. We found this integral. Let's find this integral. Maybe I will go to another page. All right, so I am finding this integral. 1/2. And I'm going to have f of x squared, so it's like e to the x squared minus g of x squared, which is just 0. So I can pull the 1/2 out, and then this is e to the 2x. So this is an integral that's hard to do. In fact, I can do this in my head. So I've got this 1/2 that was already there. When I do the antiderivative of e to the 2x, here's how I do the shortcut. Well, antiderivative of e to the x is e to the x. So with the 2 there, I'm just going to stick the 2 there. But because there's a 2 there, there's another 1/2. That's my shortcut. Something like that. So I've got 1/4 e squared minus e to the negative 2. All right, let's put our answer together. X bar, the x coordinate of my center of mass, is 1 over a. And I have to jump all around and find everything. So here's a. 1 over a times this integral, which we figured out there. The y coordinate for the center of mass is, okay, there's also a 1 over a, so let me get that out of the way. Times, times this one, the one we just found. Like that. And so we just found the center of mass. It's the point with these coordinates where x bar is this and y bar is that, like we just said. Just to return, just to return to our initial discussion, if you remember, where I pointed at this shape and we sort of made a guess about where the center of the mass looks like it might be. Of course, we got these answers, and it's hard to tell, it's hard to make sense of these answers, so I put them into a calculator, and I found that this answer is about 0.313, and that this is about 0.771. And in light of that, looking back at the picture, okay, so we shouldn't trust my picture that much, but maybe 0.3 looks like it's about there, and this is 1, so 0.7 is a little bit underneath, so the center of mass is right about there-ish. So our prediction wasn't too far off. Indeed, the center of mass, it is farther to the right than it is to the left. It has a positive x coordinate. And we didn't have that strong of an intuition about where the y coordinate is, but it's very believable. Or at least it doesn't seem like this is obviously wrong. It's believable that this is the center of mass.